All right. Welcome to the show. So how are we doing out there?
Hi, Professor. I'm doing good.
Terrific. Always nice to know I get a verbal confirmation that I figure if one person can hear me, then I know there's no problems from my end, at least anyway. So I know I shouldn't be asking so many difficult questions on a Monday, right? So too much pressure. All righty, so here we go. Welcome to the show this week. This is you're the show that's being recorded today, since I didn't record Wednesday. So hopefully you should see there's a record light there going on. So that's fantastic. And you probably saw my Blackboard announcement with kind of all the stuff going on here lately. One of them that's going to relate to this that we'll see, because a couple people asked me about that, so I'm glad I put that in the announcement, because after these two sections, if you start trying to do some of the homework, it's like the last parts of a lot of those problems relate to what's going to be in next week, because this section is 6.2, but it's one section, but it's a lot of stuff. So I have it broken down into three separate pieces in the notes, so it all falls under 6.2. So it's just a lot of content. So yeah, so we won't be able to, and you'll see when I do it, I'll show you, the one, whatever we can't get to yet or whatever, I'll go, can't do that one. So let's see if there's anything else I need to think of. I think, trying to think of what I did on Wednesday if I wanted to. No, I think we're okay. Yeah, I was trying to think of anything from last time that I wanted to think about or whatever, but I think we're good. So we'll go ahead and get started here. So in 5.1, we talked about discrete probability distributions, and we also define, the difference between discrete and continuous. But then we moved into 5.2 and we studied the binomial, which that's a discrete distribution. And this is the only continuous distribution we're going to study. We used to include the uniform distribution, but it wasn't on the agenda this time. That's fine. But there's this is the most important one by far. It's the backbone of statistics, the normal distribution. So it's the main one. But there are other ones, a uniform distribution, one called the Poisson distribution. There are other ones that are continuous. Now, it's continuous means we can't measure individual values. You have to measure them only on inequalities. We'll talk more about that later. It's not really definable at individual points very well. And I mentioned here, you see I'm talking about that many data sets are normally distributed. Let's see, let's look at some properties here. Mean, median, mode are equal. Okay, and mean's right in the middle. The normal curve is bell-shaped and symmetric about the mean. So it kind of folds right over there in half. Number 3, the total area under this normal curve is equal to 1. In other words, it forms 1 square unit. Now you might think, why is that important? We'll see why that's important. Who cares about the area? But the area is very important. The last property is not real important, but it's one of the properties. The graph technically never actually touches the x-axis, but that's, you don't have to really worry about it. It gets like infinitely close without touching it. You may remember a term from back in algebra called asymptotes. If you don't, that's okay. Don't worry. But basically it's where, you get close but not touch something. Let's see. All right. But the area is important because the area is how we're going to measure probability. And there's not going to be like a, plug-in binomial probability. It's formula. I mean, there actually is a calculator formula, but it's not like that. It's not where you precisely put in individual values. We calculate area. Whether we use calculator or a chart we're going to be using, we'll figure out areas. So in other words, the fact that this area is 1, that basically means the probability that x is somewhere between negative infinity and infinity equals 1, meaning that includes the range of all probabilities. So whenever we take out some sort of chunk out of there or something, you know, a little piece of area, that means it's going to be something smaller than 1. And because, remember, probabilities always have to be, you know, between 0 and 1. Now, we're basically taking the empirical rule and we're just expanding it to more advanced levels here or whatever. So you don't really have to worry about these individual sections on this graph here. I just wanted to show you this. This is showing the plus and minus 1, plus and minus 2, plus and minus 3 standard deviations. Now, if you look at this, when we, you know, did the empirical rule, you know, we did 68%. I don't know why they don't just use these numbers for the empirical rule. I don't know. Maybe I'll just start using them. It doesn't really matter or anything, but actually 68.2% would have been a little bit better result for the empirical rule. Not a big deal, but I mean, it's really a little bit more accurate. And same thing for plus and minus 2 standard deviations. We used 95% as the definition of the empirical rule. And every book pretty much defines it that way. But in actuality, 95.4% would have been a little bit more accurate result. Now, the last one's the same as we used. Plus and minus 3 standard deviations is still 99.7%. So you see, that kind of covers, you know, just about most of the normal curve right there. So you just about have it all covered within 3 standard deviations. But we always have, you know, outliers and things. So now let's look and see what's going on over here to the right here. Now, the normal curve is always going to have the same properties where it's symmetric about the mean, the total area is under 1. But let's look at that. I'll show you what makes the difference in these 2 particular shapes. Now, you don't have to be worried about physically constructing the shape of the graph. That's not your concern. Now, I could ask a question on test, you know, where you have to compare visually, like I'm showing you right here. But if you're just sketching out a normal curve, it doesn't make any difference how precise, whether it's taller or flatter, that doesn't really matter that much. But what actually does affect the shape of the graph is the standard deviation. The smaller the standard deviation, the taller and narrower the graph is. It's a little bit skinnier. And what makes it that way is because the smaller the standard deviation means the numbers are going to be closer to the mean. They're not spread out as far. So both of these have mean 52, basically because the mean is determined by what's in the middle. 52 right in the middle. Now, you can't determine really the standard deviations that well by looking at this, but the idea is, though, is the flatter one is going to have a larger standard deviation than the skinnier one. So that's the only thing we can say for sure, is that if you looked at those two, and which one's the larger standard deviation, it's the flatter and the wider graph. But both of those would satisfy the property that the area is still 1 for the entire graph. Well, it kind of makes sense, you know, to stay in area 1. If the graph's going to get skinnier, it better get taller to add more area, right? So to make sure it fits the criteria that it adds up to 1. So this isn't that big of a deal, but all right, this right here, thank goodness we don't really need this equation, but this is the actual equation for the normal curve over there. Pretty rude looking, isn't it? It's got everything you could ask for. It's got square roots and pi and e, and then it's got the mean and standard deviation. So yeah, that graph couldn't have just come from nowhere. You know, it had to come from some sort of equation. So thank goodness that's beyond the scope of anything that, you know, we don't have to worry about the mathematics behind all this. Thank goodness, because that can be a little rude, but that's what actually generates these graphs, is that equation right there. All right, here's just a picture recognition of just, you know, what I was just talking about on the other page. Out of these 3 graphs, I'm saying that B has the greatest mean out of the greater graphs. And does that seem reasonable? And that's strictly because it's just the furthest to the right. The furthest to the right on the x-axis means that it's the larger number, right? So that's you know, because the mean is always what's in the middle. So really it's whichever one's to the right would be the largest mean. Now, based on what I just told you on the last page, the standard deviation. Out of those three, C is the flattest of the three. So it has the larger standard deviation, and A is the tallest and narrowest, so it has the smallest standard deviation. So that's really all. That's all there is to determining that. Flattest has the largest standard deviation. Narrowest is the smallest standard deviation. That's literally it. Okay, I keep meaning to redo these graphs just because now that I could use a calculator that has color. They could both have two different colors or whatever. But anyway, this is nothing you have to be concerned with here. But I use that ugly equation that I had up there, the actual equation, and I did it for two different graphs. And then the Y2 that is using 10 as a standard deviation, and Y1 is using 5. And then, of course, I wrote these out here, so you have to trust me that I wrote out the correct one. I did, but I mean, that's why if they were color coordinated, you could see for sure which one was which. But anyway, long story short, the Y2, the flatter one, is the one that had the larger standard deviation, but not your concern. All right. Now, in any continuous distribution, it doesn't really make much sense to ask individual probabilities. This didn't occur in this. I looked at the homework. I didn't see this unless I missed something, because I've seen this come up in homeworks with various books before, where it'll ask a question in there that what's the probability that X equals something? And I would tell the students just put 0 in there. That was the right answer every time. But I looked on Wednesday and I didn't notice there were any of those in this book with this homework. So that did not seem to show up anywhere, nor would I put this on a test. But actually, if I was going to have this on a test, it would be in my review, and it's not. But so there's no going to be calculating the probability of X equals anything. These are going to be less than's, greater than's, and between two numbers. That's how that's the only probabilities we're going to find, like this. Now here's where it's going to be different than the discrete and the binomial. The binomial is a discrete, but any discrete, including the binomial, I guess is the best way to say it. In a normal distribution, let me run through all these and I'll sort of explain why this is true. In a normal distribution, the probability that X is less than or equal to some number will be exactly the same or close enough to being the same as X less than the number itself. And that couldn't be more wrong in a discrete distribution. That would be just terribly wrong. But for this, it's okay. The next one, greater than or equal to, is exactly the same thing as greater than in the normal distribution. And then betweens, whether or not you have these equals or not, that sort of thing. Let me bring up something real quick to show you. All right, that's a stupid thing. We'll go away here. Let's see. I'll even bring up the sample exams. I'm pretty sure I put it on there too. So, no, I don't need the tour here. So you're looking at this, you see the sample exam review here? I assume you do. I don't see the green bars on the outside though.
No, we just see this.
Yeah, I don't know why did that change. Yeah, that's why, because I didn't see the green bar, so I better start this and start it over again, because I think, yeah, I had to, I don't know what makes that do that. It makes me have to reshare the screen. Do you see it now?
Yeah, now we see it.
Okay, but
now I see it.
I still don't see the green bars either. That's weird. I don't know. Usually has like a green border from my point of view on the outside. Anyway, let me jump down. Where? Oh yeah, like these questions. I'm not going to go over these right now. We can do that later. I just want to make this clear to you that in a discrete distribution, whether it's this or the binomial, you know, that X greater than 3 for this problem is totally different than X greater than or equal to 3. Same thing with this one. For this, less than or equal to is totally different than less than. But I'm telling you, in the normal distribution, it is no different. I'm going to stop and reshare this because this is bugging me. I don't think me try this again. Still don't see the green border. Maybe because so you can you see my notes again?
Yes.
Yeah, I don't know why I don't see that green border. That bugs me. Okay, the reason why, as I mentioned over there, right, because it's a continuous distribution. If you think back to like algebra, you know, whenever you have something like, I don't know, but x less than 5 or something like that, in real numbers, you know, like this in interval notation, it would look, inequality, it would look like that. That goes back to algebra. When you're representing real numbers, that literally means anything less than 5, like, you know, 4.9999 would fit in that interval, as long as you didn't touch exactly 5. That's why real numbers can't be listed out like this, all real numbers in an interval, because there's infinite of them. It's forever and ever. You know, I could go 4.9999 and never stop, right? So what's happening here is if you're measuring area, I'll draw a little picture of a curve here, and you're going as close to 5 without touching 5. I'll put a little picture here, and I'll put let's say whatever's here. It doesn't really matter what I put there in the middle, but I'll just put a bar. I'll put even like dashes. Remember, dash is like an asymptote, mean you can't touch it or whatever. That doesn't really matter. So if you're measuring this area right here, if you're getting so close to 5, even if you're not touching 5, if it's infinitely close to 5, it's basically producing the same area. It makes no difference whether it touches that line or not. It's infinitely close to it. Kind of a weird, infinity is kind of a weird concept, isn't it? But it's close as you can get without touching it. So anyway, long story short, in these problems, it makes no difference, but you have to remember in the other problems, it's a huge difference. Here, it is not. So the questions, I don't remember if any of these problems, I've seen them before where they've put them as less than or equal to or greater than or equal to for normal. I'm not sure if this homework did or not. But either way, it doesn't really matter for this. But then we still have to remember that it matters for the other. So I wrote like this, you know, in a discrete distribution, especially like the binomial, for example, if you were saying between 12 and 14 and you didn't have equals at either one of those lines right there, you're talking only about 13 only. But if you put equals there, it would be 12 plus 13 plus 14. So what I'm saying is, though, in a normal distribution, it makes no difference. Any continuous, but we're only studying the normal. But any continuous distribution, those probabilities are exactly the same. So you have to kind of separate those ideas out. That's what makes it fun here, right? All right, so I just drew that picture. Now let's move on. Now I'm just making up some, here's an example. Like you could have a problem where the mean was 60 and standard deviation was 12. Mean 120, standard deviation 30. Mean 250, standard deviation 50, so forth, so on. So, you know, any normal distribution can have any kind of mean and standard deviation. Now, I'm going to use this doing the calculator, but I'm going to also show you this normal chart that we use, because to find these areas otherwise would take some kind of sophisticated calculus that we really don't want to use. So we have a chart, and we also have the calculator. We also have a chart. But if you're using a chart, which is the chart's great, but it would imply that, you know, do I have to have a chart that includes every possible scenario? Because that would be impossible. You can't have one chart for each different. But what if we had a way to convert every scenario into one universal normal distribution, you know, one normal distribution, and then had a chart for that? Then that would make life convenient. And I probably wouldn't have said that if that wasn't going to be true. So yes, we have a way to do that. And it's something you've seen before, even though we weren't using, you know, talking about normal distribution, all that kind of stuff. But we were doing, when we were doing calculating Z values before, but on the first exam, yeah, that's kind of relates to this, because the Z value is exactly what we're figuring out here. So this says we can convert any normal distribution to what's called, there's one normal distribution that has a name. This is the only one that has a name. The standard normal distribution. And for most normal distributions, we just use variable x. I've seen other letters before, but x is the best way to do it. But the standard normal distribution has a reserved letter z. It's only for standard normal. The way you know it's a standard normal distribution is your mean is 0 and your standard deviation is 1. Anything other than that is just a regular normal distribution, but it's not this standard normal distribution. Now here, over to the right, it's exactly what we used before to calculate a z-score. That's how you can convert any value, x value, from a regular normal distribution to the z distribution by using this same formula we've used before. You take your x value minus your mean divided by standard deviation. So I'm saying we have just a regular normal distribution with a mean 48 and standard deviation 8, and I just pick two different values for x and say, you know, can we convert them over to z's? If it was a standard normal distribution, what would their z values be? And once again, the z value basically measures the number of standard deviations the value is away from the mean. Sure, we can do that. Easy enough. We've done this before. So 60 minus 48 divided by 8 is 1.5. And then 32 minus 48 divided by 8 would be negative 2. So there you go. There's how you do it. Now let's start. We'll use this table. I'll throw the calculator in there a little bit. You know, it's kind of, if you get a little confused on the calculator, well, you know, I can iron out issues with you later or whatever. So, but I need to give, you know, respect to the chart here, because there's going to be people that are going to be still using the chart. Can't assume everybody's going to be using the calculator. All right, the chart, which I've already brought up, it's in the charts and tables folder, Blackboard. So hopefully you're looking at the standard normal chart here, cumulative normal probability table. All right, so what this table measures, it measures the area, which area is going to be probability, to the left of a z value. It's going to measure area to the left. Now, we're not always going to want left, but we only have this one table. We can make this table work for any scenario that we need. So, but the table itself only measures left. Now, it's a two-page table. It's got some negative z values here in this left column. And then on the second page are positive z values. So it's 2 pages here. Okay. And a whole bunch of numbers in the middle here. So we'll come back to that. So let me go back to the notes. And so I'm showing you that it's measuring to the left and to the left, whether it's negative or positive. So we're going to start out with left, of course. So this says, suppose we want to find the area to the left of a z-score of negative 2.19. So let's do that. Let's come over here to the chart. I've already got the chart snipped out right here. We'll go ahead and actually look at the full chart though. So I got to figure out, how do I find negative 2.19 on this chart? Good question. First thing you do is you go down the left column. The left column shows you up to 1 decimal place. So right over here, you see negative 2.1. The top row shows you different possible numbers for the second decimal place. So you get the second decimal place across the top row, and then you line up the appropriate column with the appropriate, well, the column where after you go down the row with the right column. Okay, yeah, so negative 2.1 is the correct row, and then here's 0.09. So the negative 2.1 with that 0.09 makes it negative 2.19. And you row meets column, and it would be right there, 0.0143. And now you can see where I've kind of circled all the numbers here. So there's negative 2.1, you know, I was like that. I'll erase that. Pretty, well, I don't know why I'm using my mouse. I got my stylus right here. Go down that way and then go this way. And there's where they meet right there. Ta-da! That was fun. Well, so much fun, we're going to try that again. Left of 1.27. All right. So I'll come back over here to the full chart. So obviously if positive, I need to go to the other page. So 1.2 is right there over to the left. There's your 1.2 row. And then you find your 0.07 column, which is right there. 1.2 meets 0.07 at this value right here. Row meets column, 8980. And here it is snipped out right there. Row meets column, 8980. Wasn't that fun? I need to get rid of some of this because I want to start using this. Well, yeah, I want to start using this -1e to the 99 here on a regular basis. So that -100, that's what I changed the notes up from last Wednesday. So anyway, that's why I'm going to do it. I'm not going to, the -100 was okay. It produced the right answer, but without using the chart, you can do it like so here. If you, and here are the command things that bring it up in the calculator, but you can go, it's in the same, it's second vars distribution, same thing as where the binomial is. Remember, the binomial is down a ways. You have to scroll down to get the binomial. You want normal CDF. We're not ever going to use normal PDF for anything. We're only using normal CDF. Now, if you're using the 83, just like the 83, it's probably just going to flash up normal CDF with the left parentheses and wait for you to put in that something in there. Now, this one defaults at -1e to the 99. Obviously, we're going to want other numbers there, and we can change it. But the way to do that is, I think I've got it in the notes somewhere in there too, I believe, but you go -1, -1, and then you go second, comma. You see it's the, if you look at that in blue, it says EE. This is just scientific notation, by the way. It's weird. It says EE, but it spits out 1E. That's correct. I don't know why they couldn't have just made it do 2 E's, or just why the calculator couldn't just show 1E, but that's weird to me. That's okay. And then put in 99. So this is basically -1 with about 99 zeros after it. So it's like -1. Yeah, you can't really give it a name, whatever, but it's, you know, it's a huge negative number. Because what was the upper value there? It was, well, I guess I don't do both of them. One of the 1.27, or either one, or the 2.19. I guess I can do that one. -2.19. I'll come back to I'll write something down on that other page here in a second. Now, if you're using just the 83, you can just put -1e to the 99, comma, -2.19, and close the parentheses right now. Now, yeah, whenever it's default, it's defaulted for 0 and 1. We're going to do some other problems later where we're going to put means and standard deviations in there. But if you're just doing this only, you don't have to, you can do that without the 0 and the 1. In other words, in fact, I'll show you. Hit enter here, and I'll go second enter. I'll intentionally go back over and delete those to show you. Same answer. Now it's, yeah. Now of course, in this one, by the time you did all this, you might have could have, you know, honey, probably thinking I'd just rather use the chart for that. That's fine. But some of the stuff we do a little bit later, you might find this a little more, you know, useful. But for that, it almost seems a little bit slow, doesn't it? But you have to be careful with, yeah, I use, you see, I used to do -100 before. Now I'm just going to go ahead and use this number consistently from here. But I got the same answer, basically. It didn't need the 0 and the 1, in other words. But what you have to, now, that's what I label. That's interval notation. So you have to be, you know, you have to understand basic interval notation to realize what you're doing here. Is that, you know, it's less than -2.19 in interval notation means this. It has to go in order also, because somebody on Wednesday, I remember, did this, and I got a negative answer. They put, for not for this problem, for something else. They put them in the wrong order. It's got to go lowest to highest, and nothing smaller. So if you, anytime you're doing less than, that always means negative infinity goes first, because you think back to algebra, that's the same as this. So it goes negative infinity. So that's what. So the -1e to the 99 is just representation of negative infinity. It'd be really awesome if they had an infinity symbol there, wouldn't it, in the calculator? That might happen down the road. But I think it'd be neat if they displayed an infinity there. It'd be pretty neat. But anyway, but that's just representation of negative infinity. So, so there. And I'm not going to redo the 1.27, but you see the answer, the 1.27. So, and they match rounded to 2 decimal places. So. But this will come in handy later, whether you want to use it just for looking up the chart, that's up to you. You can make that decision as we go. Let me go and erase this part right here. I guess I may repost the notes with this in here. We'll see. But you're going to see me use this some more again. So now using the chart, then I'll show you how to do this in the calculator also. But let's see if I did it. Yeah. Okay, there. I didn't do it with the E, the 99. Yeah, I'll do that right now too. Yeah, I probably will repost these notes. Area to the right. There's 2 ways using the chart that you can do area to the right. Because you can't just look up the value on the chart. That would not be right, because the chart only gives you left. But we can use, there are 2 ways you can do this, and both of them involve using the properties of the normal curve that I gave on that very first page, you know, the different properties. And we can use those. Now, one of them, the properties was the total area under the curve equals 1. All right, that was one of the properties we had. So we're going to use that one first to do this. So let's take a look. So let's say I want to find either one of these shaded areas. And the process that we use here is the same whether the z is negative or positive. The theory is the same. But anyway, but suppose I want that area in red. If I look up this number on the chart is only going to give me that empty spot right there, that empty area, because that's all the chart, that's the numbers that are on that chart. But if I know that the empty area plus the area that I want in red adds up to 1, I think that's going to tell me that 1 minus this blank area is going to leave the red area that I want, because we know they have to add up to 1. So empty plus red equals 1, so 1 minus empty equals red. Does that make any sense or not? I don't know. Hopefully it does. But 1 minus works. So you have to look up the chart value. You look up you don't take 1 minus whatever the z is. You look up the value on the chart, the area, and take 1 minus that number. And we'll do that here in a second. Here's the second way to do it. I like the second way better myself, but if somebody likes the first way, I'm not going to talk them out of it. We can use another property of the normal curve, symmetry. It's symmetric. meaning that so you sort of have to sort of visual this little bit of visualization. That's okay. Once you realize what I tell you what to do, you don't have to visualize this every time. But to get the basic idea, it does require the visualization of looking at this graph and pretending like it's rotating around 180 degrees. It's making like a revolution like this. Flipping around like that. It would, because of perfect symmetry, it would then look like the picture next to it here. So that's saying that the area to the right of a positive z is the same thing as the area to the left of the negative z. Okay, how does that help us? Okay, that helps us by just saying that if I want the area to the right of a positive z, all I have to do is just look up the negative z on the chart, and that will be the answer. I won't have to go 1 minus anything, because of the negative z is going to give you the area to the left. So same thing over to the picture of the right. If you want the area to the right of the negative z, it would flip around and look like this picture to the right. You would just look up the positive z. So all you have to do to find the area to the right using the chart is look up the z opposite sign of whatever the z is. If it's positive, look up negative. If it's negative, look up positive. So you've got 2 ways to do it. Well, 3, including the calculator, which I'll show you that next here in a minute. So let's say I'll do both of them for this one, negative 2.07. And I'll do it both ways. I'll get to the point where I probably won't even use that first one anymore. This part A, I'll just do it using the symmetry. So if I wanted to do it by using the 1 minus, I would look up negative 2.07 on the chart. Go back up here on the negative side, 2.07. So there's negative 2.0 right there. 0.07 is here. So it's 0.192. Now that's not going to be the right answer, because 0.192 is the area that's in that little empty part right there. We want the area to the right of that bigger chunk. So what we do is we go 1 minus that number we got off the chart to get 9808. But here's why I like the part B better, this way. Instead of doing that, if I know it's area to the right of negative 2.07, all I have to do is look up positive 2.07 directly on the table and not have to calculate 1 minus anything. 2.07. Well, I can't get the whole thing in there, but it's definitely this column right here. That's definitely the 0.07 column. So it's 9808, and then you get the number directly, and then that's the answer. Either way, though, both methods are correct. So here's the calculator. So I'm going to get rid of all this mess here and just redo this now using the 1E to the 99 business here. I guess I could do the keystroke thing in there, I guess. Yeah. All right, so these notes definitely need to be reposted. Oh, let me mention that if you're doing this with the calculator, you don't have to worry about any kind of flip-flopping or anything like that. Because you don't have to do all that mess, because we can just write it as an inequality. In other words, that the greater than the negative 2.07 is just leave it as an interval like this, and we don't have to flip-flop anything. We can do it like that. That greater than means we're going area right is okay. So the area right means greater than. We'll start talking about probabilities here in a minute, but area to the right will be just like area to the left will be less than. So let's see. So I'm going to clear all this, clear the keystrokes, and I'll just copy clear the keystrokes. I'll probably copy the keystrokes back out of there. But anyway, so it was, I'm going to go second, distribution, normal CDF. Now, this time we start with negative 2.07 because that's your lower value, and we want positive infinity as the upper. So negative infinity is negative 1 E99. Positive infinity will be positive 1 E99. So it's like taking the number 1 and adding a bunch of zeros after it, which then makes it a gigantic positive number. So we don't put net, we put just positive there, and we go second E99 at that E. Now I'll put in 99. I can leave the 0 and the 1 there. And what I said, if you're in the 83 calculator, you don't need the 0 and the 1. And you see that's going from negative 2.07 to positive infinity. Ta-da! So I'm going to snip this out of here. And then I'm going to snip those keystroke commands out of there. And then there is our 9808 answer. So I don't know how handy this is for these particular problems, but when we do the application problems in the next section, this will be a good method, and the calculator will be probably better. Well, I'll figure out the sizing on this after I copy the keystrokes in there. All right, I'll snip these out of there. Maybe that'll help if you go back and look at it. And so how do you bring that up again? Well, these keystrokes are only going to work for a greater than problem, to the right. But at least it shows you, how to get to the function and everything. So move this up here. And I'll put it right below it right there. There we go. Now, area greater than, okay, and when we do the application problems, all this is going to come back up in the next section. Less than, greater than, it's all going to come back up. This section is just primarily, or this part 1 of this section is to get you used to the concept, the theory behind the normal distribution, and then the how to read the chart. The next section will be some application stuff. Now, the area between two z values. All right. So we're going to, between two z values, it doesn't matter, it makes no difference whether one's negative, one's positive, both negative, both positive for the z's. That makes absolutely no difference. If you're using the chart, and this is good, the trickiest one's to the right, where you got to either remember to change the sign, blah, blah, blah. Here, you don't change squat. You just look up the two z values, and then you take the upper z minus the lower z, whichever one's because the answer's got to be positive. It's got to be between 0 and 1. So if you're using the chart, you look them up individually. So if I wanted to find between negative 2.16 and then negative 1.35, I drew the little picture there just to kind of show what was going on. So the negative 1.35 is the larger of the two because it's to the right on the number line. So if I look up negative 1.35, I have, going to be right here, 0.885, and then negative 2.16 will be right there. Oh, not all those. Negative 0.0154. So it's 0.0885, and then it's 0.0154. Now this is the normal CDF for the older calculator, but the same principle is going to work here, because this one is between two numbers. You don't have either of the E or the 99 deals, either the negative or the positive. It's just between the two numbers. So the only difference is, I'll squeeze it in there right below it, but so what I have down there is already perfect for those that are using the 83. It's just, so it was negative 2.16, so you don't have to put any infinities in here. Lower, uppers, negative 1.35. Oh, no. Oh. And then, yeah, like I said, so just, obviously, if it already has a 0 and 1 there, just leave it. But my point earlier was, if you're using the 83, you don't need to add it in there. All right. So I'll just kind of put that in there. So where am I going to fit this thing? I'll figure something out. Well, I can deal with that later. I can rearrange the format of it later. I'll move on now. Might shrink that one down, or okay. Anyway. All right, this one's kind of a weird one. I thought we would, usually it's just going to be less than, greater than, or between, but here's a rare case of, we won't see any application problems like this, but I think I might have put this question on the one like this on the review. I might have put a picture of a shading like that. Let's see. Yeah, I did. It's number 44 on the review. But it's, if you just have to use the basic things we just learned to kind of figure this out. So it's really not that bad. It says just find the shaded area. I could have put total shaded area, those two pieces. No problem. You just treat them as individuals. Just treat them as separate, like they were two separate problems, and add them together. I'm going to skip the calculator part on this one. You're going to see enough calculator stuff in the next one here. Anyway, I'll just do it as a chart one. So this first piece is already left. It's a left area. So left area means automatically right off the chart. So negative 1.47. I don't know. Maybe I will go. Okay, I think I will go ahead and put it. I think I will put it in the calculator. I changed my mind. Negative 1.47 is right there. 0.708. Now, for the one that's to the right of 0.68, so you see I'm already using the flip it over, flip the sign method here. I told you that's the one I like better anyway. So the area to the right of positive 0.68 would be exactly the same as the area to the left of negative 0.68. So all I have to do now is just look up negative 0.68. And so here's negative 0.6, and then it'll be that column right there, 2483. And then just add those two pieces together. So there really wasn't some fancy way that you were supposed to mingle those two pieces into one scenario. You just treat them as two separate pieces and then just add them together. So yeah, I can slap this in the calculator real quick. I would go second. Now I'm going to do this. So I'm going to do negative 1. I'm going to do negative infinity here. What was it? Negative. I already forgot the number. 1.47. And I'm just going to go ahead and put plus right here. I don't really need to get that answer by itself. Now, here's what I was talking about earlier for the greater thans, same thing. I don't have to do the whole flip-flop and all that kind of stuff, changing the sign when it's to the right is strictly for chart purposes. But I'll just treat this as a greater than. I'll start with, once again, 6.8, I think the number is. Better not guess. 6.8, okay. I'll just treat it, I'll just put 0.68 right here and just treat it as going from 0.68 to positive infinity. So now I got to put 1 EE to the 99. I don't need to do the flipping for this. Same thing, 0, 1. And is that what the answer was? Oh, this is, okay. Well,
I got it from my calculations.
yeah.
So I don't know.
Yeah.
Yeah, so I got the answer from the worksheet on my calculator.
Ah, okay. Well, I guess what's frustrating here is this really doesn't do much as far as putting this on the notes because, well, maybe I should have done them separately, I guess. Yeah, let me because yeah, I forgot about it's too much room to show it all. I should have, maybe that was the only reason for doing it in 2 steps was to, yeah, I didn't think this through very well. Um, so I'll go back and delete this one. Yeah, see, yeah, I wasn't even thinking like, oh, it's not gonna be able to show everything. So that's the first one. But I'll just have to show them like this. I was trying to be real cool there and show them in one line. Yeah, this. So I want this again. Okay. Okay. Then okay. That'll work. Yeah, I was trying to do it all in one step, which mathematically was fine, but it wasn't much benefit to show the student there, what happened. So that was only for my ease right there, but and obviously you could do it, obviously the way I did it before. Yeah, so this shows them then as just the 2 separate pieces. But obviously you saw that I could have just entered that in one line, which I did. So, but the bottom one I just treated as 0.68, comma, positive infinity. That's what it's doing right here, 0.68, heading to the right, positive infinity. Now down here, this is just introducing us into the idea of what's going to be going on in the next section. They're asking them now as probabilities, but probability is, in the normal curve, probability is area. Area is probability curve. Same thing, either way you say it. Area equals probability, probability is area. It's all just one big happy. All right, anyway. So it's basically saying the probability that your a random variable z picked at random is less than point. That just kind of bugged me because it wasn't on the same line there. Is less than 0.45 is the same thing as just, well, obviously you can use a calculator, but the quick way would be just looking up 0.45 on the chart. So same thing in the next question saying the probability that z is greater than negative 1.45. If you're using the chart, that means there were 2 ways to do it. I showed both ways. I showed 1 minus, and I showed flipping it over. Either way, it's the same answer of 9678. The last one, between 2 numbers. Oh, here's all that 100 business. I'll just get rid of that. Oh, these are for the first 2. That's confusing because I'm not using 100 anymore. But this one shows you the last one though, because so obviously if you're using the newer one, I don't think that'll confuse you because I think you know by now the 0 and the 1 can just stay there. So yeah, the 0 and 1 would just be there if you're doing the newer one, but should still be that same answer. So that just means that probabilities then are the same thing as finding these areas. Okay, there's no point in opening up the My Math Lab until after we do part 2. That's where it starts getting. I mean, I think there's first couple. I could open it. I guess maybe I could. I could do because I believe I didn't do those first couple of questions in the homework last time because I'll show you what I mean. They're kind of just this kind of stuff. They're not anything too fancy there or whatever. God, I sure wish I could make this bar not drop down on me all the time there on the top. I'm trying to add a tab here, but I can't do it. Where's that? I'm going to stop share for a second, see if that'll get rid of it. Yeah, that got rid of it. I'll come back with a share in a minute. Maybe we will do one before we go on break here. I think Wednesday I just waited till I got to part 2. So after I log in, I'll come back and share the screen. Okay, let's see. Assignment manager. Yeah, so like I say with the six, when you see 6.2 on the homework, that's actually, including all of the parts of the lectures here. So as I mentioned earlier, we won't even be through with all of it today. I have the notes posted for the next one. If you wanted to look at it, you could. But yeah, I didn't do one of these last time, but I could now, especially since this is the recorded video. Now let's share screen now. All right, so hopefully you're looking at the homework here. I don't want to do this one or the next one. I don't know. Like I said, I just skipped these. We'll see how many. Yeah, I don't want to do that many parts here because we're going to be doing these all again anyway. So. Kind of interesting. I didn't realize this one. I didn't because I didn't look at this carefully on Wednesday. That's fine, but this I will tell you, this part D is sort of like that one I drew where it was the 2 pieces added together. It was yeah, it was actually 2 separate pieces. So I'm glad that I had that example in my notes. Well, let me just do this real quick, and like I said, I'll focus on more detail. Is it all right if I do this? Well, at least can I do? Well, I can do all of it. If I do it with a chart, that'd be a little bit quicker here, I think. So I hope that's all right. So, if you want to talk calculator later, we certainly can. We can come back to this, but let me just knock this out real quick with the chart. So actually you can bring up the chart right here or whatever too, but I'll just go ahead and use mine. Less than 1.55. So less than, all I got to do is look up. Oh, if I bring up the right file, that might help. Less than is already what this chart's based on, is less than. So 1.55 would be right here. Oh, not both those. 9394. So we're doing 9394. Check answer. Hooray, yay. Greater than 1.88. Greater than. I'm going to use the flipping the sign technique. So I'm going to look up negative 1.88. Like I said, there's 2 ways to do this with a chart, and also there's the calculator way. So I'm going to look up negative 1.88. And 0301. Excellent. Between 1.55 and 1.88. All right, so this one I may just switch over the scratch. Well, I got to look up 2. No, oh, no, wait a minute. We already have. Oh, no, we can't use. Yeah, I can't use part B because that was a greater than. So so there's part A. You look them both up. It's 9394. Now I need to actually look up 1.88 here, not negative 1.88. So 1.88 is 9699. So I'm going to go in the calculator. I'm going to go 9699. Of course, obviously I could have done the normal CDF real easy. Minus, what was that answer for part A? 9388 or whatever? No, 9394. That would have been the chart value at 1.55, would have been 9394. So I subtract them. And how about 0305? You know what? Actually, because the way I showed you to do that problem for the next part, got it. Okay. The way I did it was correct, but actually the way it's asking this in the homework, I'll go over to my scratch page here. We can actually use part C to get part D. I'll show you a little trick here on that one. So it wants, let me draw the picture here. All right, there's 0. It now wants, it said to the, I'll reread the question. I'm pretty sure it said, when it said or, it means these two pieces, this, that, or that. Or means it'll be those two right there. Let me double check the question to make sure I interpreted that correctly. Is it less than 1.55 or greater than 1.88? So that was correct. Now, we can do it the way I showed you earlier, and what I'm about to tell you now, I didn't tell you before, not because I was trying to hold any information from you, but since for this problem, this will be easy for you when you do the homework, since we have already figured this out right there in the green, see, on the other one, I did the other problem, I didn't do this part first. Since we've already figured out the green part, well, green part plus red part has to add up to 1 because it covers the entire thing. The red parts, we're taking the two of them added together. So really, you definitely could do it the way I did it, like in the notes, but for this particular problem, because we've already found the green part, the answer is just 1 minus the green part. So long story short, that'll save you a lot of effort right there, won't it? So the answer for C was 0.0305. So 1 minus 9695. Okay, before I get all happy here, let's make sure I get the check mark. 9695. How about fantastic? Give me a fantastic. Excellent. I'll take it. So that was it. All right. I'll leave this up for now. We're done for that. Break time. I got 6:37. I don't know, 6:50, okay?
Yeah, that's fine.
That'll be good. Yeah, we'll get a little earlier start for the second half. That'll be good, and we'll make good time that way. So we'll start. Okay, we'll come back at 6:50, and I'll go ahead and bring up. Well, I was going to leave this here, but I could just bring up the next notes on the screen. Just leave them if you're interested. I'll just leave them sitting up there, like so. Hello again. Welcome back. I just discovered something interesting on Zoom I hadn't noticed before, that I can actually pause the recording aspect of these meetings. I didn't discover that. It's kind of nice because I've been going through and editing these things, and I just cut out the break part of the meeting. Now I realize I can just keep the meeting going, but just pause the recording. I don't have to worry about that anymore. See, I learn something new every day, so that's nice. Although I didn't discover that till about 2 minutes in, so well, I may leave it blank for 2 minutes and not worry about it, or I may take it out of there. I don't know. Anyway, all right. So welcome back to the show here, normal distribution part 2. So we all energized and fired up for another round here. That's the spirit. Okay, let's see. Calculator, I put these when I revise the notes. I kind of put this in here, sort of. You're going to see me do this in action, though, so you don't have to worry about this right now till you see me do it. But and I've sort of enhanced the calculator in the first section more than I had before, too. So, all right, so I added all this in there and just, talking about the inequalities, how they're written. In other words, because normal CDF is always written as a lower to upper value. And like I say, less than 10 is negative infinity to 10, greater than 50 is 50 to infinity, and then there's between two numbers. And here I'm mentioning the negative 1e to the 99 and 1e to the 99 as representatives for negative infinity and positive infinity. And there I have the keystrokes for both of those. That's what you get used to. That's quick. You know, you can, like here I'm mentioning, you know, you can just type in a gigantic negative number or a gigantic positive number. But once you get used to the negative 1e to the 99, the 1e to the 99, you can type it in pretty quick that way. So some of this we've already done. You know, we've already brought up the normal CDF in the last section. And so, okay, I don't think, I'll just leave that. I'm not going to read everything in here, but I just mentioned the default here is always comes up the first time is negative infinity. But when you put in new numbers in there, then when you come back and use the function again, it's going to have those same numbers that you just used the last time or whatever. But when you sort of wake it up for the first time, it kind of has this default sitting in there. Not on the 83. The 83 will just bring up normal. It won't, you know, retain any numbers. It'll just bring up normal CDF and wait for you to tell it what you want. Okay, so we've kind of done this a little bit. We're going to do it again, you know, so I won't worry about. So second vars, and that's the down arrow. Brings you right down to number 2. Second vars and hitting the number 2 probably also would do this. All right. Now what we're doing in this section is we're actually just solving some probability questions with normal distributions where we're going to have mean and standard deviation given to us. And then the idea is that we're going to be, if we're using the chart method, we would have to convert these over to z's and then get the answer from the chart like we learned how to do in part 1. So those are all z's in the first part of the lecture. Now we're going to have things where we convert them to z's. Now using the calculator, you can do this without converting them to z. But for any given problem, you'll have to, you know, you'll do lower and then upper, and then you'll have to put in the appropriate mean and standard deviation for that given problem. So I'm going to show you kind of both ways here to do this. Okay, so these are applications. They're, you know, theoretically the data is, you know, normally distributed. So what do we got? A light bulb here, and lifetimes are normally distributed with a mean 200 and standard deviation 40. And just asking probability questions. What's the probability that a bulb selected at random lasts more than 250 hours? So more than is going to be greater than, it's going to be area to the right. Once again, you know, for the normal distribution, this could have said more than, or it could have said at least, and it still would have been done the same way. Now here's the kind of the formal way to do it. So now we're bringing the calculator more into play than I used to. But here's how you would do this. If you were doing it the more traditional way, I'm going to show you. We would convert this to a z, and we already know it's not a z because the only time that you have a z is when the, you know, mean is 0 and standard deviation is 1. So this is obviously not that scenario. So we have to convert it. So we take 250 minus 200. Right there, there's a formula, and divide it by 40 and convert it to a z. So that would convert to 1.25. So the answer to this probability question will be the area to the right of 1.25. So using the chart, area to the right, remember I showed you 2 ways to do it, and I'm kind of doing these all the second way, is this is because it's greater than, we can just change the sign. So flipping the arrow changes from greater than to less than, changes the sign of the z. So all I got to do is look up negative 1.25. So negative 1.25 on the chart will be, oh, wrong page. Right here, 1056. And there we go. So there's your kind of traditional way that you can do that. Oh, wrong notes. And sometimes these answers, every once in a while, you might see them answer choices as a percentage. That's no problem. So 0.1056 is the same thing as 10.56%, just multiplying it by 100. So I could ask it as a percentage if it wanted to. So the probability that the light bulb lasts more than 250 hours, you've got a 10.56% chance that's going to happen. So here it is in normal CDF. Now see, once again, you don't have to flip the arrows if you're going to put it in the calculator. You can leave it as greater than. And notice we don't have to even convert these to Z's either. But what we do this time is we put in the lower value, which is 250. Then we put in the 1e to the 99, which represents positive infinity. Now we put in the mean and standard deviation. See, the last section, everything was Z, so that was defaulted as 0 and 1. And you put that in there and you're going to get, then you get the answer, which is here's 1056. So for those of you using the 83, when we were doing the problems that were already Z's, I told you didn't have to put the 0 and 1 in there, and that was still correct. But now for these kind of problems, you have to put the mean and standard deviation, separate them in that order, separated by commas. So now you have to add them in there. Now doing it with the newer way, you just input it and it's already going to be there. So you got to have all of those numbers there for this one, for these kind of problems when they are random variable X and not Z. So so that the chart way works fine. The here we go, the normal, you can use the normal CDF as long as you get used to the ideas, the inequalities, and don't get them, as long as you're comfortable with these. See, that was a greater than, therefore positive infinity was going to go second. All right. Let's see. So let's try it again for the next one. So you select a bulb at random, find the probability that it lasts between 180 and 210 hours. So we're still working off, that's why I labeled this part B, which, I'm not going to do this on a test, but you're used to this idea in the homework, where you have several parts to a question. So that shouldn't be too, different for you there. But on a test, I'm never going to ask. But anyway, so obviously it's still operating off the same mean and standard deviation here. So we're using the same info here. You just can't see everything all at once like you can in the My Math Lab. So all we have to do is convert both ends of the interval between 180 and 210. If we're doing them this way, we have to convert them both to Z's. And so you would take 180 minus 200 divided by 40. You take 210 minus 200 divided by 40. And you get negative 0.5 for the low end, positive 0.25 for the upper end. So using the chart way, we look those two numbers up off the chart, take those results, take the higher result minus the lower result. So 0.25. $5,987. Negative 0.5, that's obviously going to mean negative 0.50. So anytime you don't have a second decimal place, that means it's going to be right there in the first column. That's going to be 3085. Keep bringing up the wrong one. 30. So you take 5987 minus 3085. Okay, this is pretty easy in the calculator because you don't have to think about either of the infinities here, you know, whether it's negative 1e to the 99 or positive 1e to the 99. All you have to do is put the lower value of 180, the upper value of 210, and then the mean is still 200, standard deviation is 40. And then there's, you get all four numbers. Like I said, you'd have to have all four of those in the 83. I just drew a picture of it just for the heck of it. And then there it is, 2902. That will be your answer. And we're going to be doing some, you know, new problems out of the homework here in a little bit. So that's why I'm not just retyping these same ones in there, because I know we're going to do some new ones. So, so hopefully you're following what I got going here. So. All righty, Dodge Durango auto transmission gets an average of 18 miles per gallon in a city with standard deviation of 1.5 miles per gallon. What is the probability that a Durango selected at random gets more than 20 miles per gallon? Assume the mileage is normally distributed, so that's kind of, you know, thrown in there to let you know it's a normal distribution problem. There's not really much with it we could do if it wasn't, but yeah, that's just sort of there to let us know, oh, okay, normal distribution. Let's see. All right. 18 miles per gallon, nice low standard deviation. That's good that we have a small standard deviation, because you would hate to think that, you know, you don't want that to be that much of a range of values here, you know, to buy that vehicle. You'd hate for it to be, ooh, you know, it's either going to be super good or really terrible. You'd like for it to be kind of consistent. And 1.5 is a nice small number. If not, you'd have some quality control issues, I think. So anyway, so I just wrote down the mean standard deviation. Let's look at our question here. Probability gets more than 20. So that's just greater than 20. And so we take the 20, which is the x, subtract the mean. We're using that same formula right there, z formula, z-score formula. 20 minus 18 divided by 1.5. So I guess obviously if you're using a calculator, probably not paying too much attention to this part, but that's okay. Divided by 1.5. And then now here's where it gets interesting. We have to round these to two decimal places. For chart, if you're using a chart, you know, the chart's based on two decimal places. So actually this number, I believe, is 1.333333, you know, forever. So anyway, greater than means you flip it over and change the sign. So greater than a positive is same as less than a negative. So I'll look up negative 1.33 on the chart. I have this right here. 0.0198. Now, calculator. It's greater than, so you'll start with whatever number that is, comma, and there's your positive infinity. So 1e to the 99 is your positive infinity. There's your mean of 18. There's your standard deviation of 1.5. Now look at the answer here, 0.0912. Doesn't quite line up with our 0918. I said that backwards. They don't exactly match up, do they, very well there, do they? Well, what's causing that? It's not an error, no mistake or anything, but I'll tell you what the explanation of what's causing it is that the normal CDF is not just using 1.33. It's calculating that area as if it was 1.333333. So actually, it's a more precise result than you get off the chart. So your chart's going to match the calculator whenever the numbers divide evenly to two decimal places, like they did, for example, right back up here, you know, like the negative 0.5 and the 0.25. It's going to match up pretty well. But now they're going to be off a little bit here. I'm not sure if I mentioned this in the notes or not. Let me look down here. Yeah, okay, I've got this coming up. I'll go ahead and say it now, and then I'll skip over that when we get to it. I'll just say it now. But one thing we discovered last week is the good news is that the homework is set up for, I believe you can enter either one of those answers and it gives you credit. It should be. It did that. I checked it. Somebody checked it last week using the normal CDF, and then I did it with a chart for another problem, and it also gave me the correct. So I believe it works for either one of those. Now, and I mentioned that little paragraph you'll see down there, which you can read as later as many times as you want to. On the exam, you probably can expect it to be whatever the chart answer is. That way it sort of puts everybody on the same playing field. However, I always make sure that the answers are not too close together numerically. So if you do this in the calculator and get 0.912 and you're looking at a 0.918 as an answer choice and nothing else is near it, you can feel comfortable that your 0.918 is the correct answer. Now, when I say that there's going to be nothing close to it, there still could be something there, where the answer choice is, if you would have treated this problem as, let's say, for example, as a less than and instead of a greater than. That's totally different. That's a conceptual mistake there. That might be different. So, but you're not going to miss it because of this, because of the rounding is what I'm saying. That will not cause you to miss it. But that could cause you to make a mistake. Because I've had people do that, and sometimes they don't always ask me about it, but they might miss a couple more on the test and they thought they did because they got an answer, but they really didn't do it right more than anything else. But this should not cause you an issue on missing the answer. This will not cause you an issue. Just pick the closest answer to your calculator answer. That's if it's done the right way. That's the key. But anyway. Let's see. So this is a brand new story here. Monthly utility bills. Man, utility bill, I should have singular, I guess. Electric, whatever bill, one electric bill, whatever, for a certain city in April are normally distributed with a mean of 100 and standard deviation 12. I kind of want to make that singular now. You know what? I'm just going to go ahead and change it. Let's make it water. I'm not changing any of the numbers. I'll repost these, but every once in a while I just feel like I ought to change something in these notes. All right, so that's how I can if it just says bill here, I don't have to change anything else. Okay, water bill. Well, I guess that should be plural, though, after all, the water bills. Yeah, okay. That should be plural. Certain city or normally distributed, mean 100. Yeah, okay, standard deviation 12. So plural was right there. A water bill selected at random. Find the probability that the water bill is less than 80. All right. So less than, okay, I don't think the wording's too tricky here. Less than, I don't want this part to be tricky. You still have to interpret it right, but it's less than. So if we do it this way, we convert it to a Z. Oh, I got the calculator part down at the bottom. A and B both have, there they are for A and B together, same screen. Anyway, so doing it this way, you take 80 minus 100 divided by 12. And that's I think it's negative 1.66666. So it would round to negative 1.67. So, oh, Pearson, something's getting way. Okay, let's see. I had to wake up the homework there. It doesn't like it. So look up negative 1.67. And we have wrong column. This one, 0.475. That will be our answer using the chart. I keep bringing up this. 0475. Let me scroll down. So here it is in the calculator. It's less than. So less than means it always starts out with negative infinity, finishes at 80, and 112 are your mean and standard deviation. So it's a little off. 0478 versus 0475. Not too bad. Some of them are going to be able. Next one, part B, is a little more off than that even. But once again, just pick the closest answer. But the homework appears to accept either one of them, which is good news. Yeah, this one's off a little further because you've got rounding issues for both of these numbers. So that's what really throws it off even a little bit more. Okay, between 95 and 128. $95 and 128. So for 90, so there's how you write between. 95 less than x less than 128. You know, the equals don't matter. They don't have to be there. So you convert both of these to z's if you're doing it this way. So it's 95 minus 100 divided by 12. And then 128 minus 100 divided by 12. And rounded, I got negative 0.42 for the low end. And then I got 2.33 at the high end. And we've been doing it this way. You look up the chart. So 2.33. Positive 2.33. Right there. 9901. Negative 0.42. Negative 0.42. $3,372. And there's 3,372. You subtract them, you get 6,529. So the normal CDF, you put in 95 as your lower, 128 as your upper. There's the mean and standard deviation, 6,517. So like I said, that's strictly the rounding of the z's is causing that. No errors whatsoever. It's the rounding of the z's to use the chart that makes the answers different. So nothing to worry about there. I think I did a part C and a part D here also, yeah. And there are those two calculator answers. And greater than 138. Okay. Greater than 138. Convert that to a Z, will be 138 minus 100 divided by 12. It would be 38 divided by 12, which rounds to 3.17 using the chart. Now greater than, using the chart means you flip it over and change the sign. It makes it less than. You make this, if this is positive, this becomes negative. So you look up negative 3.17. And there it is, 0008. All right. Now I did another greater than, I'll show you why in a second. What's the probability that the bill is more than 85? So it's another greater than. 85 minus 100 divided by 12 is negative 1.25. Now because it's a greater than, I flip it over and make it positive. I'll look up 1.25. It's 8944. In my experience, the reason why I kind of wanted to do two of these like that is because sometimes students will ask me, you know, they're trying to, maybe they're not using the calculator. If you're using a calculator, you probably don't care, probably what I'm about to say, but the way they word it, they'll go, oh, okay, so it's greater than, especially after doing this example up at the top. So it's greater than, you take the negative, you make it negative, or the way they say it kind of concerns me because they might mean the right thing, but when they say make it negative, that bugs me because I want people to make sure they know that means you make it the opposite of whatever it is. So if it's positive and it's a greater than, then it becomes negative. If it's a negative, it's greater than, then it becomes positive. Now that might be what they meant when they said it, but if I hear it, I'm going to go, it means, so if somebody says, make it the opposite sign, then I know they know what they're talking about. But I don't want somebody to think that if it's negative, it just stays negative, in other words. No, if it's greater than, it becomes the opposite of whatever it was. Okay, that's why, because just sometimes I want to be sure when somebody asks me that I'm interpreting what they mean. But here in the calculator, no problem. These are both greater thans. No flipping was necessary at the greater thans. You start, the first one was 138 and the second one was 85. And they both have the 1e and the 99 because they're both going to go towards positive infinity. And then the first one, that's just scientific notation with negatives. So really that number is 0.00077, which the 77 then would just round that. Okay, I'll just write it like this. It's really this number, but if you round it to 4 decimal places, it would round to 8. That way, when you round this to 4 decimal places, it would be 0.0008. All right, and then there's the bottom, and you can clearly see is the 8944, so there's no trouble there. So, all right, so here I'll leave that there for you to read. Bob, okay, I mentioned about the homework, and I mentioned that exam. It's probably going to look like the chart. Okay, there we go. And you can look at that later, and yeah, I just put this in there recently, so if there's anything confusing about what's that about that, just let me know. This one, I leave this one in there as sort of what I call kind of a fresh problem, for lack of a better word there. I'm going to leave this there. Now, keep in mind, I'm not going to save the work I write here. In other words, that answer will still sit there, but that way if somebody, you can write it down if you want to. It's up to you. You don't have to do anything you want, but this will not be in the notes at the work I write out here. So it kind of gives us gives me a fresh problem to work with. So I'm going to kind of not write it as neat as I normally do, but it'll be legible. Don't worry. 49 minutes is the mean. Standard deviation 16. It's asking the probability that you select a person at random that spends more than 60 minutes. Okay, it's kind of interesting because this problem, it was old. I got it from, I forgot some book, but many, many years ago. I finally changed it like a couple of years ago because what the problem was before, it said person spends reading a newspaper, which that's kind of obsolete. Some of you might still have like grandpas and stuff that kind of read the newspaper. I don't know, but but I said, well, this is pretty obsolete, so let me change it to something a little more modern times here, Newspaper, what in the world's a newspaper? Anyway. All right, so there we go. So it looks pretty well set up. So I'll set this up as the chart way if you'd like to see here, but I don't know. Everybody here might just be doing it calculator. I don't know, but just humor me for a second here. So it'll be 60 minus 49 over 16. Not that this takes that long, but I will do the normal CDF. 11 divided by 16. So let me see whatever that is. Point something. Who knows? .6875. So I'm going to round that to 0.69. Okay. Okay, so if I'm using the chart, I just flip that over. Obviously, even if you're using the chart, you don't have to really write out the formalities of this. Negative point. Let me draw this over here. So 0.69 would be somewhere to the right of 0. There we go. Looks like that. All right, I'm going to look up negative 0.69. Okay, so negative 0.69. It's going to be all the way to the right of this negative 0.6 row, all the way to the right. There it is. I'm not going to write that down because I already have the answer written down, but there it is, 2, 4, 5, 1. So I've already, that way if somebody, you know, went and looked at this later, they could try to, even though I'm not saving these notes, they could do it themselves if they wanted to. 0.2451. So let's put this in normal CDF and see what happens. Sound like fun? So if you're just waiting for that, you can wake up now. So it's going to be, this one's going to be a greater than, so we can kind of leave this, except that's going to be, was it 60 minutes? Oh, 60 minutes, I believe. Yeah, 60. There's my one. Okay, this happened to already be set up the way. Just like, because remember, it's just, it keeps the numbers that were already in there from whatever you put in there previously, unless it brings it from scratch. 49, I believe, was the mean. And no, wait. And 16 and 49 and 60. Let's see. I'll make sure I put them in the. All right, I had it. Yeah, that was it. Should have trusted myself. 49, that was going to be 16. So let's take a look at that. Okay, as not surprising, that's a little off, but we did it right. 2, 4, 5, 9 versus 2, 4, 5, 1. Once again, that's just the rounding thing or whatever. So that's correct. Wasn't that fun? All right, let's see what we got down here. So do you think it would help out just every once periodically? I don't know how often, if I just like let out a random scream and then just went back to normal, just sort of see if you were dozing off or not, or no, maybe not. Like if I just went, ah, but a lot louder than that, and then just start talking normal again. No, that'd be kind of mean, wouldn't it? I wouldn't want you to spill your beverage all over your computer or anything. So, all right, so suppose, let's see, well, I forgot, I got this data from somewhere. I forgot where. I didn't actually make these numbers up. Some of my other problems are all made up, but this one I got from somewhere. SAT math scores are normally distributed with a mean of 518, standard deviation of 115. So what percent probability of the scores are less than 500? Now, the key on this is finding the percent of all scores less than 500 is the same thing as calculating one score, the probability of any one selected at random. That's telling you kind of the same thing. So the way the wording looks like, it sounds like it's going to be a different question, but it's not. If you just calculate the probability that any one person is less than 500, you are then counting the percentage of all that are less than 500. So, okay. So I don't know, then want the wording to trick you there. So other than that, it's pretty straightforward. Less than, straightforward. So 500 minus 518 divided by 115. So it's negative 18 over 115. So negative 0.16. Keep bringing that one up. So, okay, see, this is a less than. So sometimes people get so excited about that flip-flop thing, you know, got to flip-flop it. That's only when it's greater than. You got to pay attention to what less than, don't do anything to it. Leave it alone. It's only when it's greater than. Some people get so fired up, they're focusing on that flipping thing. That's already less than. So that's if you're doing it this way, of course. If you're doing it calculator way, you don't have to worry about it, but don't flip anything. Another thing to be careful about if you're doing the chart method. I've had this happen with people before. Confusing, and they just had like a brain fart. You know, they just, instead of like negative 0.16, they were looking up negative 1.6. I'm not saying for this problem, but like a similar type problem. why am I not getting this answer right? And then they go, oh, that's all. Oh, then you get frustrated, obviously, when you know it's something simple like that or whatever. But yeah, negative 0.16 versus negative 1.6. But so this is negative 0.16, 4364. I know it's got to be frustrating that something, yeah, it's one thing if you feel like you're struggling on something, and if it turns out it was challenging, that probably makes you feel a lot better than if it was just something like that. You know, it feels like it's frustrating, like, you're kidding me? That's all it was? Okay, so there we go. We would expect about 43.64% scores to be less than 500. All right, here's a new little wrinkle here. If 1,500 math scores are randomly selected, about how many math scores would you expect to be less than 500? All right, nothing too fancy here, but this problem is similar to, well, not the way we got the 0.4364, but now that we already have that result. Now what you do with it is exactly like the problem that was on the first exam, the pie chart problem where you had to take whatever the percentage was and multiply by the total. That's exactly what you do here. So all you have to do is take this percentage that we calculated, the 4364, and you multiply it by 1,500, and then you just round to the nearest whole number, because obviously the number of scores has to be a whole number for tests there or whatever. So yeah, you just multiply it by the total. So it was really not that bad. Here's the normal CDF. Okay, now this is a little bit off because I used the chart number here to get 655. I used the calculator here, which produced 657. But there, there's the negative infinity, there's the 500, and 518. You can't see that all the way to the right, but that would have been the 115 for the standard deviation. So that's why it's different. Here's an interesting dilemma. I don't know if this comes up. I avoid this for exam purposes. I don't know if it's going to come up on the homework or not. But suppose you get a z-value that's off the chart. If it's off the chart on the low end, even though the chart stops at 0, 0, 2, you can use 0 even. That's fine, 0 or 0, 0, 0, 1 or whatever. That doesn't really matter because the chart's negative 3.49. And so anything beyond that, you could treat as whatever. It won't affect anything, either 0 or 0.0001. Hopefully that won't come up in the homework, but if it does, maybe it will not care too much. So the same thing on the positive side, even though it stops at 9998, you can either use 9999 or just use 1. So I don't know if that's going to come up. I'm curious now. I'm going to do this in the calculator. I'm going to do for negative 3.49. I want to do negative infinity to negative 3.49. So that means this is the area to the left. And then I'm going back. Now I'm going back to 0 and 1 here. Now I'm going back. This is the z right here. So I'm changing that back to 0 and 1 because it's a z. All right. So that would be the 0, 0, 0, 2 right there. Okay, so that's where that's coming from. All right. But you 0, 0, 1. Obviously, the farther negative you get, it's going to change. I'll change this real quick. If I go, like say, negative, I'll just do negative 6. Oh, well, okay. Look at that. That's got a bunch of zeros in front of it. That way you can almost just use 0 at that point. But I mean, yeah, so it's yeah, so 0, 0, 2, so 0, that's not gonna hurt you, I don't think. I wonder what it is for like 4. 4, it might be 0, 0, 0, 1 or something. We'll see. It's 4 zeros in front of it. So anyway, all right. Not gonna hurt anything, no harm. I'll avoid that on a test, but I think if it comes up on a homework, hopefully it shouldn't matter too much. So okay, that looks like that's it here. So I must have really trimmed this up and made it a lot more, I did trim it up a little bit, made it more efficient. So I'm glad we're recording this one instead of last Wednesday. So all right, the good news now is we'll just pop over and do a little bit of homework and we'll call it a week. Middle of October. Feels like the semester is almost over, doesn't it? Maybe not. Probably from your point of view, it doesn't feel that way, does it? We're on a really good pace here. I was looking because like I said, you saw it, you read that announcement I posted. We had we're going to have time for an entire review period, as we will for the third exam also, and still finish the material, no problem. Yeah, I think it's taking it's doing the exams outside of class time. It's really saving us a lot of valuable time. Okay, so we kind of played around with these. Let's go over here to the applications. So hopefully you're looking at the homework screen. Just tell me if you're not. I'll assume that you are. But
We are.
Thank you. All right, now here's what I was talking about. A couple of people had asked me about this, and I'm not going to do it today yet because I haven't covered that material. I mean, you want to read ahead and try to figure it out, but if not, you can just wait. So I know it's probably kind of frustrating, but you can do some of these. Like part D on this problem is based on what's going to be seen in part 3 next week. That's probably kind of frustrating, but I guess it lets you move around, right? Couldn't you do like if somebody wanted to, they could do A, B, and C and then go to the next problem, right, and come back. Is that right? I mean, you should be able to. But and it'll probably ask you, right, if you want to leave the question or whatever, or something or another. So all of those, like I'll look ahead here. So it's D and that one, probably the last one in every one of these. This one, let me bring up. Oh, this one has a lot of parts to it. So the wording is I'm going to make the wording a lot better on the test than it is. And these are tricky, but yeah, C is that way on this one. And so is part of D. All right, that one's kind of weird. Part D on this one fits that category. And then C and D. Wow, you know what? I'm looking at part D here on this one. Yeah, I want to remember to do this one next week. I must have taken these out of the notes. I'm almost tempted to put this back in here in the notes. I'm going to put this recording. I'm going to keep the Zoom meeting going, obviously, but I'm going to put the recording on pause for a minute here. So now, so yeah, that's what it was. It was this problem with this part D, the professor thing. That's what we got to wait. That's that. So C and D for this one would also be next week. So you can't do all of these just yet. I mean, unless you self-study and want to try to figure it out. But I'd wait if I was you. I mean, because like I said, even when I put the deadline dates, which I guess I will, probably be a few days after the exam ends. But then I'll be opening up again a few weeks later, right near the end. So at least you'll have all the knowledge you need by next week to finish the problems. But it wouldn't hurt to try to do some of these parts. But at least you would know why you would be confused. There would be some logic to it. So those people that emailed me about it, they had every right to be confused. I don't know what's going on here, part D or whatever. So let's do this though. We'll do A, B, and C on this one, then we can try another one. Okay, I'm going to go ahead and snip this over to a scratch page, so I don't have to keep going back and forth. I'll go ahead and take part A with me here. Okay, annual per capita, da-da-da-da-da, is, okay, that really didn't mean anything, but that's, I hate when I put extra info in there, but okay, here comes the mean and standard deviation that we need. 33.6. And then standard deviation is 10. So that's important. All right, probability. More than 39. Okay, so that's not too tricky. Probably someone consumed more than 39 gallons. All right, now, since this, we always have kind of a small group for these, about a dozen people or so. I'll just check and see here real quick. And obviously, when I was doing the lecture on this, I was going to show, both ways. Obviously, that's important, but it's up to you here. Do you want to see it both ways or just the calculator way? So if someone wants to see it both ways, don't feel embarrassed, and no one's allowed to boo you or anything like that. But if you want me just to do calculator only, I'll just do that. It's up to you. So does anybody need to see me convert it to Z, look it up on the chart?
No.
So I'll assume no answer means no, in other words.
Yes, no, so just the calculator.
Okay. Yeah, then you can change your mind on that. That doesn't mean your answer's set in stone here. So you might think, maybe I do want to see it that. It's up to you, because I figure there's no point in showing it if no one, in such a small group of 12 cares, then, But I didn't give you a choice during the lecture because it's important, because obviously other people are going to be looking at this. But this, even though, well, you got to be here to make the decision for this. You don't have any influence now. The other, I wanted to do it so people could see it done both ways, but you control the viewers here. The live viewers control what happens here. So sorry for those folks that look at this later and don't get to see it. That's all right. But they got to see other examples. Are you ready? So it's going to go more than means I'm going to start with normal 39, normal CDF. More than means I'll start with the 39. I'll go to positive infinity, which will be 1E99. The mean was 33.6, I believe. I obviously should have written that down. I got scratch paper right beside me. I always keep paper with me. So obviously when I hit enter, you'll still see that there, but there we go. So I'm getting 2946. 2946. But like I said, if somebody is using the chart later that comes look at this, I think whatever that chart answer is, if it's different than this, should still work. I tried it for a couple of problems at random. I don't think I did this one, but there could be a bug in the software, or maybe it doesn't work for something. I don't know, but I hope so. Yeah, the calculator actually makes this pretty efficient, because every time you do the normal CDF now, you don't have to, for these multi-part ones, you don't have to enter in the mean and standard deviation anymore. So between 30 and 40, not too bad. Calculator does kind of make it fun, doesn't it? But the greater thans and less thans, you still got to pay attention, though, to the order you put in there and stuff. So there's 30. Here's 40. I'll delete those two. And same mean and standard deviation. How about that? Let's see if that looks right. 3795. Part C, less than 30. Okay, we can handle that. Less than 30, any less than, means I now have to start with that negative infinity. It must go first. So it's -1 e to the 99 0.3594. Oh, wait. Ta-da! All right, here's some bonus learning here. Without explanation, next week will be the explanation. You'll get the explanation next week. I'm just going to put this, that way you can always go back and watch this. I'm going to put the calculator part in there for this one, even though I haven't taught it yet. So don't worry, you're expected to be confused here. Bonus learning. But next week will be the actual learning. New function. 33.6. Yeah, it's that function right below normal CDF. I just felt like doing that. I'm sorry. I apologize if that's confusing you, but what does it want for an answer as far as 56, 86? Let's see if I got it right. Fantastic. That will be learned next week. But hey, I guess if you just look at those keystrokes and watch what I did there, you can do it. But you got to be careful. Yeah, the left-hand grade. We'll go into more detail about this next week. The other problems might work differently. This one just happened to work this way. So don't assume what I just did. Okay, let me look at one. Okay, this one has like 5 billion parts. I don't want to do that. Yeah, it's too much of that percentage stuff. Let me jump ahead here. I might come back. We can do the truck one. Okay, this one is very similar to the one we just did. That would be a good one. I can go back, but yeah, this one, part C, the command I use would be a little bit, the input would be a little bit different than what I just showed you for that part D. So that's why you might want to wait until you see the lesson for that, because the 0.25 is not going to work for that one. This looks good. No, either the next one or the last one was good too. It didn't really matter. Similar idea. So we're bringing up some new numbers. I guess I don't really need to cut and paste. I'm doing is, since I'm not writing it out, let me just go ahead and write down the mean and standard deviation here so I can not have to try to worry about memorizing it. So the mean is 18.97 gallons and standard deviation of 4. Beautiful. Let's see. All right. More than 12 gallons. Okay. So like I say, we're not looking for the wording of these to be too tricky. You just have to obviously pay attention to your inequalities. So let's go normal CDF. Let me double check. It did say 20, right? 12. I had the mean and standard deviation written down. So lower is 12. Upper is going to be 1 EE to the 99. Mean is 18.97. Standard deviation is 4. I like 9593, assuming it's 4. Should be 4. Yeah, 9593. I guess you can't assume anything with this, but 4 is the common for this because 4 decimal places is what you would get if you were using the chart. So you never know this sneaky thing. You know, it's fooled me a few times when I expect a certain number of decimal places, and it won't ask for more than 4 for this, but it could ask for less. How about between 5 and 9? Okay, I think that's going to be all right. So I'll put in 5. Remember that between, we don't need either one of those infinities. Between 5 and 9. 5 is the lower, 9's the upper. Enter. But you see, if you're using a TI-83, you ought to see that you're typing them in there, no problem. How about 0061? Fantastic. Less than 9. Once you get the hang of this calculator, it's pretty fun, isn't it? Obviously, you need to make sure you get the hang of it yourself, you know. Me having the hang of it doesn't really do you much good, but I think you'll be all right once you just try it yourself, obviously. So you got to start, upper was, let me make sure, was it 9 again? I think it was 9. Yeah, less than 9. Obviously, the upper was 9 in the last problem because it was between 5 and 9. Lower, negative infinity. Upper is 9. Same mean, same standard deviation. So that's the same thing as saying less than 9. 0063. Oh, okay, 0063. Ta-da! Oh, heck, I might as well do this one again, too. You're going to see this again next week. You know what? Actually, so it's okay. You don't follow, but that way, this will be good because that way I don't have to go back and do these problems necessarily because I'm going to do those new problems, a couple ones I saw in there, the one that had a bunch of parts to it. So you'll see this done again for sure anyway. So, but like I said, these percentages, this isn't going to be the right way to do this for it's going to be slightly different from one of the ones I've already looked at there. I believe it was the next one. It's all about the wording here on this, but I know this one will work the same way as the last one. And like I said, this will all become more clear next week. Because this is important that it's less than here. Yeah, for this to work right, the area has to be left. But you're going to get all that good explanation next week. One thing I will mention, even though without going through the theory behind this, is if you want to try this using the TI-83 just to get your check mark and move on, that word left does not have to be in there, and I'll talk more about that next week. But if it's in there like this, you just leave it, don't worry about it. But you would not have to enter that left thing in there. Those other numbers, though, would have to be in there. Yeah, I just want to mention that. That'll be, fully explained next week. Is it 2 decimals again? Well, I'm still assuming it will be 28.28. Yeah, so at least if you are going to try this, like I said, I want to at least mention that. So you go, I don't see no left in there. Yeah, and then we can do these other ones that have the percentages next week. So I don't know. You think we can go ahead and stop the official lecture here? Is that okay with you? I'm going to stick around for like other questions, but So we're going to do this. We might as well save some of this for next week too, right? So,
Yeah,
so
we can.
That's that. Does that sound good?
Yeah, that sounds good. So we could
Imagine
do
time to warn it. So I'm just going to, let's just go ahead and stop the official lecture. And now